All right, let's see if the audio is still good. Beautiful. All right. All right. And I am back. We are back. Um, so today we want to talk about or over the next, this is another one like my last set of or last section 3.1. This is section 3.2, and I'm definitely gonna have to split this into several videos, just because of my schedule right now, more than anything, but it will take a second. Um, and so in the last section, we are talking about measures of central tendency. So we're talking about, and again, you'll kind of see as we go through the course how important those things are. But basically, we got some data. What is the average? What's the middle? What would we expect? But a little bit like we talked about in previous videos, so the important things the important things that we need to analyze data is not just the middle. So the middle does tell us a lot, sort of, again, like I said, expectation. Um, but we know that all bits of, I mean, if you think about all the bits of data that we've analyzed so far, that we've, graphed or whatever, obviously all the data wasn't in the middle, right? So the middle tells us something, but it doesn't tell us the whole picture. In fact, we've been, again, getting graphs going of this data and then commenting about the distribution of the data, the shape of the data, right? So those shapes, whether it's a bell curve, whether it's a skewed left, a skewed right, a a J shape, the J left, the J right, uniform. Um, think about all those pictures. Yeah, sure, there's a middle, but there's a lot going on outside of the middle. And sometimes, that the left and the right end, so wherever the middle is, the left and the right end kind of tail off pretty fast, but sometimes they don't. And there's a good amount of material area and therefore data and things going on outside of the middle of the data. Um, so we need some way to kind of measure. So we can't just measure the middle of data so that we have sort of an idea of the expectation. We also got to measure, well, how much of the data basically is not in the middle, or maybe a better way to think about that is not necessarily how much is not in the middle, but on basically on average, how far is the data away from the middle, or how much of the data strays away from the middle. I think strays away from the middle is kind of probably the best way to think about it. So we need something that measures how much does the data stray away from the middle? Does it hold tight and close to the middle, or does it spread pretty far from the middle? Spread is a good word. So how spread out is the data away from that middle? And so that's the second thing we really need to get a good analysis of data. How far does the data stray away from the middle? How far does it spread from the middle? And so we need a way to calculate that, to measure that. Again, like I was talking about in the last video and the previous videos, it's nice to have sort of a rough idea in your head, but now what we're trying to do is we're trying to knock down ways that we can definitely measure and say something about. So last set of videos was the middle of the data. This is going to be about, we need to be able to make a definite claim about how far or how much does the data stray away from the middle. And so the way that we measure those, there's a couple different ways we can measure those, but that um, that quality that we're going to measure, how much does it stray away from the middle? In statistics, we call that variance, basically. How much does it vary from the middle is the idea we're trying to get across. And there's a couple ways that we measure that. So what I want to do, kind of my usual, let me get some data. I'm either going to write it up on the board or project it, whichever. But let me get some data up and let's talk about different ways that we can measure, the different ways we can measure how much that data varies from the middle. So give me a second here. Well, let's see, what do let's try projecting it and just see. It's always more about how much room do I have and how much room do I need. So let me see how it was projected. think we might start, I think we might start with 9 here. All right, so, and give me a second. So am I gonna have enough room or well, honestly, really don't want to rewrite all this, so I think this will be fine, at least for now. Let me try to. Like this, okay. All right, so the data we got right now, the following data shows the price of silver and the price of tin over a recent 9-year period. On the range, the variance, and the standard deviation. So we're going to talk about these three. These are not the, let's see, we're at 3.2. So these are not the only measures of, well, yeah. There is one other thing that I consider a measure of variation that some of these books call it a measure of position, but we'll talk about that. That should be in either section 3.3 and 3.4. So these are not the only measures, but these are pretty much the three standard, no pun intended, but standard measurements for variation. How much does the data vary from the middle? Range, variance, and standard deviation. So let's talk about a little bit of what those mean and then how you calculate it. The range we've actually already talked about. So I kind of included it. It was included in a previous section. But if you think about it, so range again is highest minus lowest. So that's one way, I would say kind of a crude way, but nonetheless, that's one way to say how much does the data vary from the middle, right? Just basically say, well, forget the middle. Let me give you the distance between the high and the low. So that's one way to find how much does your data vary from the middle, is range. So again, just highest minus lowest. And we could do that for both silver and tin here. So what I'd like you guys to do really quick, just silver and then the range of tin. So it's easy calculation. Go ahead and just take a second to do that. Pause on your side, I'll pause on my side and go ahead and figure that out. Like I said, easy enough. So looking at silver, I'm trying to find what's my lowest, what's my highest. Looks like 7.34 is my lowest. Highest is 35.24. So over these 9 years, silver has ranged in price of a high of 35.24, low of 7.34. Subtract those, and what you should end up with there is 27.90. So the range of this data is 27.90. It's ranged literally. So that's actually one of the meanings of the word range. It's ranged $27.90. And then the range on 10, 483. Is there something now? 483 is the lowest. What's my highest? About the highest, I think so. So, or 10, that's gonna be, it's ranged from a high of 1575 to a low of 483. And let's see, that's gonna be 11.1092. So that's a range of $10.92. Good. So tens has varied in price $10.92. Now, so notice that neither of this method of doing it, so this method of figuring out, how much your data varies or strays from the middle, doesn't even really reference the middle. It's just saying more like, in this case, tin has gone, the distance in the tin price or the amount the tin price has changed over these 9 years is at most $10.92. And then for silver, it's 27.90. So somebody might ask from this measure of how much your data strays or spreads from the middle, somebody could ask which one varies more, which one which one has varied more, tin or silver, and what would you guys say? It's pretty obvious, it's silver. So silver has had a lot larger spread in price, so the price is more variable, which means maybe silver is not the better bet as far as if you want to invest, right? So if you wanted to put money in a metal, that you would want to in the future. So this was over 9 years of time. So you're sort of using that to try to predict for the future. And that can be an issue of itself because there's nothing about these 9 years that says the future is going to be exactly like that, right? Um, but we do this as humans, not just in economics, but we do this in general, we even in just everyday life, right? So you go through some life experiences and then you say, well, the future should be like that roughly. So I'm going to use these life experiences to make a guess, to inform myself, to make a guess about how I want to deal with those future situations, right? And of course, those futures situations are invariably, they are somewhat like our previous situations, but they are different. So we hope that on the fly, when we're in that future situation, we can figure out how it's different and then make adjustments there, right? But we need a base to compare against. And so we always compare to the past, even though there's no guarantee the future is the same as the past. But that's all we got, right? So same thing in economics. Say I'm trying to invest. When I say invest, what I mean is put some money away something, right? Or some business and let them do their thing. And then basically what I want is I want to pull more money out later. All right. So um if I'm actually I guess you could look at this two ways. So if I'm investing money, if I'm gonna buy a bunch of silver or a bunch of tin, um I would like to see the average price go up over the years on whatever I'm investing in. And if you think about it, then you want your variance or you want the spread of the data to be pretty low, right? I don't want to invest in something that has a huge variation in price because what if I catch it at the wrong time? So again, I'm assuming the future is going to be like the past. So I'm assuming in the future, it's also going to vary roughly like this. Well, what if it's a bad year and that price goes really low? Then my investment doesn't pay out really well, right? But if it's a good year, then I will say it does pay out not only just well, it pays out way better, right? So there's some risk in investing in something like silver because maybe it's a bad year and my investment totally didn't pay off well, or maybe it's a great year because there's a $27 swing and my investment pays out pretty sweetly. Right. But maybe it's safer. So the idea is this is risky, but maybe it's safer to invest in tin, assuming that the average price of tin goes up consistently over the years because the variance is less. So even if it's a bad year, it's not going to be that much below what I would expect to be able to sell it for. And so I'm still going to make a good profit off that, right? I'm gonna make a good payback over whatever I initially paid for that tin, whatever I initially invested. So when you're picking safe investments, things that basically what we're saying is I want to make a bet with myself that I'm definitely going to pull out more than I put in. We want things with less, whose measure of variation less, whose in this case range is less. All right, so that's how you calculate the range for our set of data here. Um, however, it was a leading comment, but nonetheless, I made the comment that this is kind of a crude way to tell, how your data is spread out. One of the reasons is, I mean, maybe crude's the wrong word, but well, let me get back to crude. But one of the things about this is tells you nothing about the average. So again, I don't just want to know when I'm analyzing data, I don't just want to know what the total spread is. I want to know how much does it spread from the middle, because again, so a range assumes that the highest and the lowest are kind of meaningful and it's something that I'm looking at. But most things tend towards a middle, right? They tend towards an average. You get your highs and your lows. You know, you get your really good year and your really bad year, but most years are going to be in the middle. So more what I want to know is how much does my data kind of spread and vary, not from the between the poles, but from the middle, right? And range doesn't tell me anything about that at all. So there's a functional thing on range that it doesn't tell me something that I need that's important for analyzing data and therefore using the data to, again, like we're talking about here, make predictions for the future, tell me where I'm going to invest, etc. It's no reference to the middle at all. So we need a measurement that actually references the middle. It tells me how far the data is spread from the middle. The other reason I say this is crude is it is just about absolute numbers. It's a high, it's a low, like it's just it's just total spread, right? And there's a lot of details we've seen with our diagrams that if you just look at the numbers without getting a whole distribution going and looking at the details of that distribution, you miss a lot of the details in there. And those details, again, actually are important for analyzing what's going on with the data. So this is kind of when I say crude, I say it's crude because it just papers over the details and just says high and low, right? So ultimately, this is fine, but it's really not great for a lot of analysis we need to do. We need a measure of the spread that one takes into account the middle and has some nuance to it. It involves the details. It doesn't just go high to low, right? Um, and so what we're going to talk about next is we're going to calculate what's called the variance. So the variance is what statisticians kind of came up with that does both. It references the middle. So once I get my variance, it's going to tell me something about the spread from the middle, but it's also you'll see uses then the details of every bit of data and it just gives us some more nuance and detail about how this data is spread than you would get with something kind of crude like this. So let's look at variance, and you'll see kind of really standard deviation. But I'm going to title this variance. How do I want to title this? But you'll see we'll get to the standard deviation as well. And give me a second. I'm looking at the video there, and it's looking like well, I think that's just the board. This looks pretty clear, but let me make sure just do a little, and you'll focusing on this to make sure this looks as crisp as we're gonna get it. That's fine. Be a little crisper. Sure. All right. And so when we do this, we're gonna do variance and standard deviation. We're gonna start with the silver data. So right now, just kind of don't pay attention to the tin data. All right, so we want to calculate what's called the variance of this data. So like I said, what we want is we want something that references the middle. We want to basically figure out how far is the data spread away from the middle. So we need a distance away from the middle. So the first thing we're going to do when you build variance is, since we need a distance away from the middle, we need a middle. And we just talked about in the last section how to find the middle. You can find the middle using the mean, the median, the mode, the midpoint. We saw often that the midpoint is not a good play. So we were left with kind of three things really that tell us the middle, tell us possible middle. So either mean, median, or mode. I want you to remember from the last section that median and mode basically neither of them had a calculation associated with them, right? There wasn't a formula that gave you them. We saw in several examples that honestly the median, um, I think in a lot of situations, the median probably is closer to the real middle of data than anything else. At least it's, the mean oftentimes is good, but when the mean is good, you'll see the median almost always is about the same. Anyways, so if I was building a way to calculate variance, I would use the median, actually. Problem with the median is there's no way to calculate it, right? You actually have to list out the data and find the middle, and so it's all completely a visual thing. So when statisticians were coming up with variance, so the first thing we need with variance is we need to figure out for each data. So what we're about to do is we're going to look at each data point, and like I said, we need spread from the middle. We need distance from the middle. So we need a middle. And when they were looking at this, I think they probably had, as far as I can tell, they had the same thought as me, is the median is probably the better play most of the time for the middle. However, there's no formula for it, and they needed something they could reliably calculate every time. So statisticians, when they came up with variance, they decided that the middle they were going to use was going to be the mean. Not because it's always the best middle, but because it's the one we can calculate every time, basically. So the first thing we need to do when calculating variance is you need to figure out the mean of this data. Um, um, so we need to figure out the mean of this data. So that's the first thing we're going to do. And again, now that you already did the last section, you know how to calculate this. I want to get you sort of involved in this process. Also, because then when you have to calculate this yourself, if you're calculating this by hand, this is what you actually need to do. First step is figure out the mean. So go ahead and pause on your side. I'll pause on my side, and go ahead and figure out the mean really quick for silver. Sweet. So we know for the mean, you want to add these all up and divide by how many there are. So actually, let me do this really quick. By the way, somebody did point out on the first video for 3.1, I divided by 9 instead of 11 for the mean. And that was wrong. I needed to divide by 11. So that's my fault, y'all. So just, you've already seen that video. You probably noticed that and just edited it yourself, but you can go back and make that edit. But anyways, so 1, 8.25, 10.45. Two 46. It's like 172.46. We're dividing that by with 9 years. So this one, this one we are dividing by 9. And so what I'm getting there, so your mean here, let me see too. So it doesn't matter how you represent like a symbol for the mean, but they do have a symbol for the mean in this section. So let me find which one they're using. They're probably going to use it for the rest of the book. So at least help us write it that way. Okay, let's they're doing that. Also, let me check on something. Depending on the statistics book, they introduce one idea sometimes earlier, sometimes. I think they do. Let's go back to them. Sorry, so we're gonna divide that by 9. So as we go through these problems, we'll kind of make we are gonna make a distinction between population means and then population variances versus sample means and therefore sample variances. So the first thing I want to tell you about that is as far as when are we going to talk about one, when are we going to talk about the other? Just we're going to talk about one when the data shows us the whole population. We're going to talk about the other when we're taking a sample from a population. So for instance, this data is the silver prices and tin prices over 9 years. The 9 years is our only amount of time that we're considering. So this is the whole population of data. It's just all the data that you could get on this thing, right? So that'll really be the difference. Is we're gonna see some situations where they're gonna take a sample of the data. So they'll say the word sample a lot of times, but even if they don't, you know that there's a bunch of data and they're taking some of it, right? So if you take some of it, then that's a sample, whereas if we've got all of the data, that's a population. And so the difference that you're gonna see it make for us. So we already talked about how you find the mean, for instance. You add them all up and you divide by how many there are. However, when you have a sample of data out of a population, when you do your mean, you don't divide by the total number, you divide by the total number less 1 or n minus 1. So if n is all the bits of data, then you would divide by n minus 1. So for instance, if this was a sample of the silver prices over a much longer period of time, but I only wanted to use these 9 years, then my mean would actually be all of this added up, not divided by 9, but by 8. So by 1 less than how many there are. And I think for this level of class, it's hard to, they do a pretty good job in the book of actually trying to describe why they do this, but for this level of class, it's hard to describe why you do that. But basically just know that when you take a sample out of a large population of data, because that sample in general is usually small compared to the data. So for instance, think about, elections, right? They'll do a survey of about 2,000 people out of, what we have, I think it's like 60 million registered voters in the US, something like that. So you have 2,000 person sample out of 60,000 or 60 million people, right? Since that sample is so small compared to the large population, when you divide by, in this case, if you took a survey and it had all these values and you divided by 2,000 people, the surprising thing is that tends to underestimate. Basically, it doesn't match the population average. So it doesn't, when I say it doesn't match it, it consistently goes under it, basically. So if we actually were able to survey all 60 million voters and get their average response to some question, right? Then when you do the 2,000 people, for that sample, if you divide by 2,000, that's actually going to underestimate the true average by a little bit. And we see this consistently. So what we do is we divide by 1 less. There's several reasons for it. There's some theoretical reasons that I can't really explain well to y'all in a class like this. But the practical reason is if you think about, if for instance, if you take 20 and divide by 5, that's 4, but if you take 20 and divide by 4, that's 5. So let me say that again. So if you take the number, it's like say you added all your stuff up and you got a 20, and there was 5 in that sample. If you divide it by 5, 20 divided by 5, you get a 4. So you would say your average, your mean is 4. But since it's a sample, if you divide it, you want to divide it not by 5, but by 4. So 20 divided by 4, notice that that gives you 5. So notice that by dividing by 1 less, you've actually upped your average or your mean by a little bit. And basically what we see is for large populations, dividing by 1 less than the sample size is enough. It bumps your average up enough to really match the population average well. So I don't know. So that was a lot of talking. I kind of didn't. Hopefully you could see that in your head, or at least you could see the numbers and the words and kind of the ideas and catch that. So when we start working these problems in this section, they now are going to factor in whether you're dealing with a population or a sample. So again, if you know the whole population, you do exactly what you've been doing. You divide by n, the number of things. But if it's a sample, you'll see not only for the mean, but you're going to see for the variance and standard deviation, we're going to divide not by the total sample, but 1 less. And again, what that does is it just sizes up our mean, and it'll size up our variance and standard deviation enough to kind of match what we'd expect from the population. Anyways, so this is not a sample though. This is my whole population over 9 years. These were my prices. So when I find my mean, I'm going to divide by 9. And what I'm getting here. So the symbol that they're going to use for a population mean is this, it's a Greek letter named called mu. Don't ask me why. That's the letter I actually don't know. Usually for a lot of algebra stuff, I know why they use one figure or letter or another. For this, I have no idea. But this is the symbol mu, and mu is going to be your population mean. And what I'm getting there is 19.16 rounded. So that was a very long. Here's your mean. So again, we're going to use this as the middle of our data. So again, so then what we're going to do to calculate variance. Again, my goal with variance is I now want to figure out, basically want to get an average spread. So the way you want to think about variance and standard deviation is what it is an average spread away from the middle. So the first thing I need to know though is how far, if this is my middle, I need to know how far each of these numbers are away from the middle. So I need to know what is the spread away from the middle. So to get variance, what we do, so right now pretend that this is the first column in my table. So this will be the first column in your table, and you can use that to find your mean. And then the second column, so pretend that that's not there. The second column is going to be distance from our middle. I think this marker is going. Oh, this marker is good. So we need a column. In this column, what we're going to do is we're just going to take each of these numbers and subtract mean from it, so we can figure out literally what's the spread. How for each piece of data, how far is it spread away from the middle? Because again, my overall goal, I need something that analyzes the spread from the middle. So it's dependent on the middle, and we calculated the middle. And now we're going to calculate the distance away from the middle. So for each of these, the 2380, for instance, I'm just going to take 2380 and subtract subtract 19.16. And what do you get there? So 2380 minus 19.16, what is that gonna give you? Just kind of do that really quick. What you should get for that is what, 4.64. There is a word for this, so that I want to label this as distance from you. So when you're looking at this example, you kind of know what to do. So again, we talked about it early on in one of the lectures. Anytime you want the distance between two numbers, you just subtract. So subtraction is our way of finding the distance from one thing to another. Just like we subtracted for highest for the range, for highest minus lowest. So the distance of this number from here is automatically subtraction. So I'm hoping that if you see this wording, it'll tell you what to do and you can use that as your example to look at. The word for this though is deviation. This is the deviation from the mean. That's just what they call this. So then for each of these, that's what you're gonna do, is you're gonna take the next one, you take 31.21 minus 19.16, and then 35.24 minus 19. So you're gonna figure out the distance from the mean for each one of these bits of data. So let me have you do that. Again, it's subtraction, it's easy enough. You guys easily got this. So go ahead and pause on your side. I'll pause on my side. Figure out the deviation distance from the mean or all the rest of this data going down the row or the column. Okay. I don't know. One of these. I don't know. All right, but easy enough. We just got to do some subtraction. So I'm not going to write out. I'm not going to write out all the numbers just because it'll start to get crowded. But we're going to do 31.21 minus 19.16, and that's going to give you. So the second one here should be 12.05. And then 35.24 minus that is 16.08. And then 20.20 minus that is 1.04. And 14.69 minus that. So when you got to 14.69, hopefully when you subtracted this, you didn't take away the negative, because that is actually important here. Because again, when we're thinking about when we're thinking about how far the data is away from the middle, it matters if it's higher or whether it's lower, right? Because that's a different place physically in our distribution. So again, if you had a graph of this data, it would be to the right of that middle rather than to the left of the middle, or higher versus lower. And those are different results. Those are different, it does mean something it means something different if you're 5 higher than your average versus 5 lower than your average, because what I got again, your values, not just where you are in the diagram, but your values basically mean something entirely different. And I want to know am I riding, for instance, is my Honda Civic gonna ride higher? Are the miles gonna be higher than the average that you get out of a Honda Civic engine versus being below? So again, that's actually a good, better, more practical example. So let's say we know the average, engine life for a Honda Civic, like that, very general, but a Honda Civic. It matters if my particular Honda Civic is going to make it 50,000 miles over the average versus 50,000 miles under. I got to plan a lot differently, right? 50,000 over means I've got, maybe a couple years over the average before I even have to plan money to start replacing things. 50 miles under means that's a couple years before when I would have expected to have to start planning and saving money to replace things, right? So it makes a huge difference whether it's below or above. So I'm saying all that to say then we need to note and keep track of that difference here. So when you do 14.69 minus this, that needs to be a negative. So it's gonna be negative, let's see what, 4.47. That's gonna be a negative 4.47. 15 is gonna be a negative 4.16. 13.41 is gonna be a negative 5.75. 11.57 would be negative 7.59. And 7.34 is gonna be even farther into the negative. That's gonna be negative 11.82. So these would be, so when you're calculating variance and deviation, you're gonna have your original column of data. The next column is always gonna be your deviation. How far is that data away from the mean that you calculated? So the general idea, or the general kind of, again, concept we're going for variance and standard deviation is again, I need something that measures what's the spread, what's the typical. So the idea is, what's the typical spread away from the middle? So here's all the individual spreads, and like I said, we need those details. What we're gonna now do is find an average of these spreads. Because that's kind of what we're looking for on average. So not everything sticks in the middle. And maybe it sticks close to the middle, maybe it sticks far. That closer, that far is the spread we're trying to measure here. And so not everything sticks in the middle. So on average, how far is it away from the middle? Again, is it small? Is it big? What's that average spread away from the middle? So what we're gonna do is we're gonna find an average of these deviations. However, before you just go and add all these together and divide by how many there are, calculation wise, another problem that the mean falls, so, when we're finding the middle of this, that's what we're gonna do is we're gonna find the mean. But another problem that the mean has calculation wise that we didn't talk about in the last section, because it just doesn't come up naturally with most data, is that when you find the mean of a bunch of numbers, but a lot of those numbers are negative, basically your average that you get actually undercuts the true middle, the true middle of that data by a lot, not just by a little, but by a good bit. And it's because negatives and positives, when you add them together, they kind of like, what do you call it, absorb each other, so they tend to go towards a middle. So if you have a bunch of positive numbers and a bunch of negative numbers and you add them together, you're almost always going to get something close to zero. Even though if I did a graph of this data, especially because we have some large numbers, both high and low here, the middle of the data may very well not be near zero. But because of the way adding together positive and negative numbers work, your mean is almost always going to be close to zero. So once you get your deviation, you're going to have some negative numbers. And so unfortunately, we can't just add all these together and divide by 9. Because you're going to get something close to zero almost every time, and that's not necessarily what the average is. So instead, what we're going to do is this next column, what you're going to do is you're going to take the deviations we just got. So deviation, and you're going to square all that data. And so what they're trying to do here is we know that adding together negatives is going to give us an issue as far as finding an accurate average or an accurate mean. And so essentially the thing is, if we could get rid of these negatives, then we'd be good, right? And if you think about too what deviation means, it means distance from the center. Again, what we're doing is we're trying to find an average distance away from the center. So that's what variation, and you'll see what really standard deviation is. It's an average distance away from the center. We also know, so I was making that big deal about it does matter whether it's positive or negative, but we know that the word distance means positive, right? So for instance, this negative 4.47, that deviation is telling me that this bit of data is 4.47 under 19.16. But in terms of distance, it's 4.47, right? So in terms of finding an average distance, I really do need these numbers to basically be positive. I still need to take into account that they're under, but I need these to be positive because that's what we're really trying to say. It's that far away from zero. Anyway, so statisticians, when they were coming up with this and they looked at this, they needed a way to basically turn these positive. Now, one way to turn them positive, and honestly, the better way to do it would be to do an absolute value. So you can take an absolute value of these numbers, and that just makes them absolute value. The absolute value of a number is how far is it away from zero? It's a distance question. So the absolute value of all these numbers would be just be the positive version, and then we could add them all together and divide by 9 and be good. And the problem with the absolute value, unfortunately, is that when we try to program computers to do it, so basically when we try to program a machine to do it, the absolute value is actually pretty hard to program. So they didn't use absolute value. It is mathematically, it is the better one. So they call it absolute deviation when you use absolute value. So mathematically, it's the better one to do, but it's a lot harder to program. So instead, what they did is they used squared. At first, maybe that doesn't make any sense, and I think that's fair. But if you think about it, if you take a negative number and you square it, what do you always get? Good, you always get a positive number. So squaring is just another operation we have mathematically that basically always returns us a positive number. So what we're going to do is we're going to square not just the negative numbers, we're going to square all these numbers. That way we're going to end up with all positive numbers that represent now not the deviation, but the deviation squared. So not the distance away from the middle, but whatever that distance is squared. So, but that's what we're going to do. So for instance, this 4.64 that I got here, all you're going to do is 4.64 squared. And that's going to give you a long, number. 4.64 squared. It's 21.5296. So that's going to give me 21.5296. Notice that unfortunately, when you square numbers, they get pretty large pretty quick, right? So that was a 4 and some change that we were squaring, and you end up at 21 and a half, right? 1.6 really. But okay, so we're going to square. So that's 4.64 squared. So what you're going to go through and do is you're going to square each of these numbers. And that'll give you deviation squared. And then I'll show you from there what we're going to do to figure out variance and standard deviation. But let me have you do that first. So go ahead and pause on your side. I'll pause on my side. Go ahead and take each of these deviations, just square them so that we got all positive numbers. All right. Let's see what you guys got. Let's see what you guys got. So let me actually. So I don't have a calculator with me. Let's use the old phone calculator. Do that too. So the 12.05 squared is 145.205. 2025. 16.08 squared is 258.5664. 1.04 squared. $1.0816. And then negative 4.47 squared is 19.9809. So again, notice with the negative number, it gives us what would have been the positive distance squared, but it gives us the positive number. It's a negative times a negative is a positive. Let's see. 6 squared So 4.1 or negative 4.16 squared is 17.3056. And 5.75 squared is 33.0625. 7.59 squared is 57.6081. Then negative 11.82 squared is 139.7124. So these are all my deviations, my distances away from the middle squared. Now, so again, notice that it turns them all positive. So then what do we do with that? What are we really getting at here? So like I said, what I want is I want an average distance from the middle, an average spread from the middle. So then what we're gonna do is we're gonna find our average deviation squared, and the average deviation squared is your variance. And by average, you know, like we talked about in the last lecture, that's a middle. So by middle, I'm going to be using mean. So we're going to use mean find means the whole way through this, just because calculation wise, it's predictable and we can calculate it every time. So the next thing we do then is I'm going to find the mean. I'm going to find the mean of these. I'm going to add them all up, divide by 9, figure out the mean. And that's your variance. So your variance is not it's basically the average of the squared distance away from the middle. So it's not the average distance away from the middle, it's the average distance squared away from the middle. But that's the first thing we're going to find here. So and that'll give you the variance. So take all these deviation squareds, add them all up, divide by 9, and we got it. So I'll give you a second to do that again. So pause on your side, I'll pause on my side, and I'll actually calculate it on my side this time before we come back. But let's find the mean, the deviation squareds, and that's the variance. Let's see what you guys are getting. So when I add all these together, I get 694.0496. I want to save some space there, so I won't write it. But I get that number, 694.0496. And then since this is a population, I'm going to divide by 9. So what I get for the variance here, and again, I guess we'll round it to 2 decimal places, is 77.12. And that's my variance. Variance, the symbol they use for that in this book and probably majority of books is S squared. There's a couple different symbols they use for it, but this gets used maybe more often than others. So on average, so what we're trying to say is on average, these data points, you square the distance away from away from the mean, they are on average 77.12 squared, just squared away from the middle. Now that gives you the squared distance, but I think the one thing to think about is, well, but I wanted to know, you know, our goal was to know not the square distance, but the actual distance. So what is the average actual distance, like away from 0, not squared? So how do we get to there from here? So we had to square these. We squared these to get rid of the negative, to make a reliable calculation way to get rid of the negative. So we end up with this average squared distance, which we call variance. If this is the squared distance, how would we sort of undo that? How would we get back to the normal distance without squared? Basically, what's the opposite of squared? And so if you remember, so when you square something, you multiply it by itself. There's an operation that does the reverse, where you find what times itself gives you a number, and that's called square root. So square root is the opposite of squared, just undoes the process for you. So what we're gonna do is we're now gonna take the square root of this variance, because then that will undo the squaring of the distance. So now instead of the average squared distance, if you take the square root of that, it's now just the average distance. So we're gonna, this next, it's not even a column, but we're just gonna take the square root of our variance. And that's gonna give us the actual average spread, average squared distance away from the mean and what we've been trying to get at. What is the average spread? So how far is the data on average spread away from the middle? So that'll be this next thing here is we're gonna take the square root of the variance and let's do it as a class. So we got 77.12, really it's 77.1166 and a bunch of twos, and it's but we're gonna take the square root of that. So let me see if I can get my calculator to do this. Yes. Okay. But we'll take square root of 77.12. And what I get there is, again, rounded to 2 decimal places, 8.78. And this number, so again, the average squared distance is variance. The average actual distance is called the standard deviation. Deviation means distance away from the middle. So this is the standard deviation, standard way to calculate it. And if you think about it, if variance is s squared and we're taking the square root of that, then what do you think? What symbol do you think they use for standard deviation? Exactly, just s, because square root of a squared takes it squared away. So the symbol for that is s. Good. And that is your standard deviation of silver data. So what that means is we can say the spread of the silver data that on average, silver varied from the middle from $19.16 by on average about $8.78. So we'll get into more details about percentages later on in this section, but again, so in some sense, what we're trying to say is on average, my data was kind of, or maybe we can say kind of half the time. It actually ends up being more than half, but half the time we're saying our data was either $19.16 plus 878 and or $19.16 minus 878. So we could almost create called an interval, but you could always almost create this little zone where you're saying on average, my data should fit either 878 below the middle or 878 above the middle, either 878 below that, which I think is $10 and change, or 878 above that, which is almost $28. So yeah, so on average, my data's, kind of, you would expect it to spread from about $10.50 to up to about $28. So good. But that's what we're looking for. So standard deviation is the main way that statisticians basically answer the question of not what the middle is, but what do you call it? How much does my data tend to stray away from or spread away from the middle? It tends to spread away about $8.78, either positive or minus. There is something else that they bring up in this book. So basically using the range, is that really true? So they have a way for a range where you can sort of approximate the standard deviation. So you should never use this honestly as your calculation for the standard deviation. But in certain cases, this approximation for the standard deviation is pretty close and it's based on the range. So let me, yeah, actually this You don't talk about this in a lot of stats books enough that let me confirm. I think I know how to do the approximation, but let me make sure I'm getting it right. So where is this? Let me also see, this may only be for samples, actually. Check on this. Variation, we'll get to that. Samples. I'll pause this for a second. Let me just find it really. Okay, yeah, so it isn't, so they use this little approximation, whether you're looking at a population or or sample. So there's something called the range rule of thumb. And what they're trying to say with this is, again, this is an approximation, this is not anything exact. But what they're trying to say is most of the time, a lot of the time, if you take your range and divide it by 4, that is approximately standard deviation. It's close to the standard deviation. So you'll have some homework problems where they ask you to give the approximate standard deviation using the range rule of thumb. So that's all I'm trying to kind of prep you for here. But let's see how close it is. So the range we got for silver was 2790. Let's calculate this. So 2790, and we're going to divide that by 4. And if you take 2790 and divide by 4, what do you get? So again, oh, you know what? I'm sorry, guys. They did -1 here. They considered this a sample. That doesn't make any sense. That's okay. But if you take 2790 and you divide it by 4, you get 6.975. Which, I mean, yeah, it's sort of close to the standard deviation there. I honestly, I think this is a little far off personally. But they're going to ask you to calculate this approximation to the standard deviation using range divided by 4. So I just want to show you how to do that. So yeah, sure, that's approximately close to that. Okay. So if you're looking at a population of data, this is how you calculate kind of your variance and your standard deviation. We'll see this on the next example. If you have a sample of data, the difference is every time you do your means, you're dividing by, again, n-1, you're dividing by 1 less. So like when we added together all these deviation squareds, and then found the mean, so you add these all together, you would be dividing by 8 instead of 9. And so again, what that does is it makes the number artificially just a little larger, which makes it match the population information better. So actually, that's why I looked at the answer here. They treated this like this was a sample rather than a population. Which I guess I sort of understand why, but I don't know. I would disagree with them. But nonetheless, so the answers you're gonna see there were calculated by both your your mean being divided by 8 instead of 9, and then which would have given you different numbers, different number for the mean, different numbers here. but then when you square them and you divide, you were dividing by 8. So it ends up a larger number. So if you look at the answers they give here, so if we treat this as a sample and we divide by 8 instead of 9, then you end up getting for silver your so the range is the same. We know that your variance is now 86.756. In the book, what they're doing is they are rounding to the next decimal place. I'm just being a little lazy and rounding to the same decimal place as our data. So also, if you're in a chemistry and physics class, though, you would never round to the next decimal place. So I'm sort of between worlds is what I'm doing. But anyway, sorry. Stay long. Oh my goodness. But notice we got 77.12 by treating this like a population and dividing by 9. So, but if you treat it like a sample and divide by 8, both here and then here, you're gonna get 86.756. So your variance is slightly higher, decent bit actually, almost 10 higher. And then notice, because of that, when you take the square root of that number, your standard deviation is also higher, 9.314, which is again, a little substantially higher than what we got. So that's the difference. So if you know from the problem that it's a population, you'll divide normally like we did in the last section by how many there are. If it's a sample, then you're going to divide by 1 less. Weird, why did it pump open? That's okay. All right, so that's your first kind of taste of doing variance and standard deviation. That's really what we needed to get out of that. So a couple comments. This is an obnoxious process. And you could put this data into an Excel spreadsheet or put it into your graphing calculator and it will calculate these things for you. I'm not going to go over how to do that. Part of it is because I don't know, it's just that's one of those things that it's a tool, whether you're using Excel or using this calculator, you can use a calculator on the test. So it's a tool. So it's just figure out how to use the tool if you don't already know how to do that. But I will say that on the test, when we get to the test on this, I'm not going to give you a ton of these to do, probably just one. I want to know that you know how to calculate it, basically. So I can't say that you can't use the calculator, but I would like, since I'm only going to give you one on the test, I would like you to actually physically calculate it out like this. The real advantage, and I'm not saying you should calculate it physically like this every single time you ever have to find a standard deviation, but the advantage in this is that the standard deviation, again, it means something. It means your average distance away from your mean, from your middle. And you physically see that when you do this process. You calculate the middle, you subtract square to get the deviation squared, to get the variance, and then you undo that squared to get the standard deviation. So it's like by doing this, you really do, like, you physically see that it's the distance away from the middle. Whereas, unfortunately, you throw this in a calculator and you press the button, you know that's what it means, but you don't see how it's created. So basically on a test like this, I would like you guys to see how it's created. I know that you can use the tool. I know that you can figure out how to enter in that information and press the button combinations to get the answer they're looking for. So on coming for a test like this, again, I'm only going to give you 1 or 2 of these to do. So I'd like you to calculate it by hand. But all that said, I know it's an annoying process. It's the reason we have computers and calculators is stuff like this, where if you had to do this a lot, it would just take up way too much time. So you won't have to do it a lot for the test at least. But so see if you can crank 1 or 2 of these out by hand. All right, so that'll be the end of this video. I got to move on to a meeting, but I'll come back for the next video, and we'll either start with another example like this, but maybe for a sample. Yeah, so I'll figure out, or we'll move on to kind of the next thing. But I'll see you guys for the next video.